Learning to Convolve, the Generalized Weight Tying Approach by Nichita, Diaconu and Daniel Worrall of Philips Lab, University of Amsterdam. Trivial as it may seem, these two images contain the same dog, but shifted horizontally. In terms of pixel values, however, they are numerically different images. The label, and so the task of classification, is translation invariant. Exploiting known invariances, or more generally, symmetries in learning is an old idea, and it underpins convolutional neural networks, or CNNs. A key feature of the convolution is that translations of its input result in translations of its output, as we see here. It turns out that up to a basis change, this is the only linear map with this property, which is known as equivariance. Mathematically, the convolution, which funnily enough is actually a cross-correlation, is a collection of inner products of an input f with G-translated filters. The field of equivariance is dedicated to developing generalizations of the convolution to new classes of transformation, such as rotations or flips. The simplest convolutional generalization is the group convolution, used to model symmetries under invertible transformations. The basic premise is to take an inner product between the input f and transformed versions of the filters, which we write using the operator L sub g. We have just replaced translation with another transformation. So, for rotational convolution, we might rotate our filters 8 times, say. Here we show 8 rotated 3x3 patches using a nearest neighbour interpolation scheme. But herein lies a problem. Is this a good model for rotating discretized images? Perhaps a bilinear scheme would be better. In our paper, we show that equivariance is actually broken under both of these transformation schemes. To fix it, the transformation operator L sub g must be unitary under the convolution. This is a definition of unitarity. It says the inner product from which the convolution is built is independent of the transformation operator L sub g. In other words, it must be norm-preserving. It is not entirely obvious how to build such a transformation operator in the presence of discretization, so we present a scheme where this property is learned. We represent our weights in a filter basis, with coefficients psi hat and basis elements e. A transformation of a filter can be implemented as just a transformation of the basis. The coefficients psi hat are invariant to the transformation. This is reminiscent of weight tying. But we are still left with the problem of how to transform the basis e while preserving unitarity. For this, we present an algorithm to learn both e and all its transformed versions. We use a system of regularizers to achieve this. In a preliminary experiment, we wanted to see whether we could just learn translated filters. We built an MLP, and the resulting weights are shown here. Essentially, convolutional structure has been learned in the fully connected setting. Using this learned weight tying, the MLP halved MNIST test error from 1.4% to 0.7%. For reference, a typical CNN achieves about 0.5%. Visualizing how a filter is rotated in this basis, surprisingly the off 90-degree rotations are not perceptually pleasing. Compare these filters with nearest neighbour and bilinear schemes, but it turns out that these filters lead to far more stable activations. We trained a CNN using different rotation schemes on the CIFAR-10 dataset without data augmentation. Here we monitor the validation error on the vertical axis as a function of input rotation along the horizontal axis. For all rotation schemes, the validation error fluctuates. In our scheme, the error fluctuates in 4 periods, reflecting the 4-fold symmetry of the imaging grid. Our rotation scheme, called partial, presents the least validation error fluctuation in all rotation schemes we looked at. Thanks for listening. If you want to find out more, you can visit Daniel's website or come and chat with us at ICML at the given time and location.